I think you can get started now.
Yeah, thank you for that kind introduction. Hi everyone. My name is Tamás Deme, and this is going to be a talk about mixed reality in aviation. So let's get started. So as I mentioned, my name is Tamás. I come from Budapest in Hungary. I've been a Windows development MVP for quite a while now, and work at a company called Vim at the moment. Not the text editor, but a different one. We do construction stuff. But most of the work I'm going to show you, most of the things I'm going to talk about is coming from the company I've worked at before Vim called the 360 World. We started in 2016, I think, when the first HoloLens sort of became available. We managed to get the first one in Hungary. And we were also interested in, developing not just mixed reality, not just HoloLens solutions, but also VR things. So the entire journey that I'm about to talk about is started out with this very simple concept, having a VR headset control a pen tilt zoom camera. So I'm gonna show you a short video. Hopefully it's somewhat playable over the stream, which is sort of like an advertisement on what this thing was doing. Let's see. You shouldn't be hearing music, by the way, because I turned it off. So we called it the smart binocular, and I will tell you what exactly it does after the video ends. All right, so the original project idea came from the Hungarian air traffic control entity called Hungara Control, and they had this problem that if you imagine an airport with having just average airport tower, not all parts of the airport are visible from the tower because you might have buildings, hangars, something that's blocking the view of the controllers. So what they wanted was to get a camera that they can, move around in these locations where they can see. And essentially, we wanted to move from just having a, monitor and just some joystick or something to having something that's more natural. So we came up with the idea of having a VR headset that we are going to modify to act as a binocular, and we will going to synchronize the movement. So as you are moving the VR headset, it's going to move the camera along with it. And our plan was to build this with Unity, with ASP.NET framework at the time, and connect all this together so your movements will get synchronized with the camera. So as we got started doing this, we obviously run into a bunch of interesting problems, and I think most of my talk is going to be about these interesting problems. First thing, I don't know if any of you had any experience with these security cameras that we could use, but they are not really designed for the very precise and smooth control that you sort of expect from, using a binocular. Like their movements are usually very strict, like you can move them in, vertically or horizontally at once, maybe in a 45-degree angle, but doing smooth movements was mostly out of the question. And it took us quite a long time until we have found a camera that was really expensive to begin with, but it had this advanced API that let us control it, not by specifying a position where it should move or not by specifying a direction, but giving it essentially a velocity. So when we were tracking the movements of the person, we weren't even exactly giving points to where to look. We were just directing the velocity where the lens should move, and with that we managed to make a pretty smooth experience relatively. Also, as you saw in the video, we wanted to put the labels on the airplanes that you're looking at, and it is really hard to match a real life camera lens with a game engine, because the game engine camera should act like the real one if you want to make sure that the labels appear in the locations where they should be. And the third thing is that we had to modify the VR headset itself, so it would be, an easy to use device as a binocular, because normally it has the head strap and everything. We didn't want all that. We just wanted to to hold it up your head, look around, and then put it down. And so we originally used a first generation Oculus headset, like the original one that you would plug into your PC, and we took it apart completely. We had designed a case for it with a bunch of buttons, and we used Arduinos inside of the thing so that we could essentially have extra buttons, as you saw in the video, on the top of the headset that let you like zoom in, zoom out, or move around in the menu. And a fourth problem was not making people sick while using this. Now, as you might imagine, in a VR headset, if what you see doesn't match up with what your, the accelerometer sort of, the stabilization stuff in your ears say, just like in a car, if you sit in the back of the car and you are reading a book or something, you get sick very easily. We experienced the same problem because as you moved your head quickly, the camera was slow to catch up. So people got sick very quickly just by using it. So we solved this, as you see in the picture, by having a black background, having a floating video feed that was always where the camera was actually pointing. So if you move your head quickly, the camera feed just sort of like slid in front of where you were looking if it was just catching up slowly. So this solved the part where you would get sick, but we've also had to make sure that if people were using this device at night, we didn't accidentally blind our users, because, for example, the Oculus software has a message that you can't turn off if you've been using it for too long, and it's just giant bright white message saying, hey, you've been using the device for too long, maybe you should take a break. But imagine that you're working at the air traffic control tower at night, like your eyes got used to the dark. You put on this headset and suddenly it's a blinding white message that, hey, you shouldn't do this. And this actually happened once up in the tower. And we've made an air traffic controller not see for a few minutes, which is not something you should do really. Thankfully, it was at night and there isn't that much traffic at night at the airport. But still, it's something that we had to care about and we had to sort out. And honestly, I don't even remember how we solved that one, but it was something that we had to mess with. And then to actually get the data that we are using is also a very hard process, because even just to get access to the tower, we had to go through like a security check by the government, just so we are allowed in there. And even when we got access and we could go in there, the data feeds that we received were very interesting. So these are very, very old formats invented in like the 90s and 80s, where if they could save a single bit by having a different one toggled, they did. So I spent a lot of time figuring out this format called asterisk, which also gave the name, by the way, to our projects. I don't know if you've heard about this French asterisk and obelix characters. So we decided to call our project Obelix because it handles the asterisk format. And we also had this key takeaway that assumptions are dangerous, and this happened because we had consultants working with us during this project, and they sort of assumed that we know a lot of things in aviation, and we sort of assumed that they knew a lot of things about our programming and how these things work. And just to illustrate two key examples, the data that comes from the radar dishes that that gives us the information about where the planes should be, as it turns out, the altitude in that is not the actual altitude of the plane. If planes take off, they reach this place called transition altitude, around like 3,000 feet high, like 1,000 meters ish. And then at that point, they change their altitude system. Nice. So at that point, they changed their altitude system into the same altitude system that's like covers the entire Earth based on a set barometric pressure. I don't remember exactly what the pressure was, but essentially from that point on, they don't measure the altitude from how high up you are from the ground. They measure the altitude to that barometric pressure, and this makes sure that anywhere in the world, if there are two planes, they always know their altitude compared to each other. Because if someone would be, flying above a mountain and it says, hey, you are 1,000 meters above from the mountain, but then someone else is 1,300 meters from the ground, which is not the mountain, they might actually be on the same height. So they do this that the airplanes avoid crashing into each other and everyone agrees on what the altitude should be. But as you are landing, they change to a local height, local altitude. But this doesn't happen in the radar data. Like the radar data is always going to give you the barometric height, the barometric altitude. And because of this, we had airplanes that in our view, they went underground as they were landing, and we were really, looking at what's going on. Why is the label, going underground? And then we were looking at the altitude reported, and it was like minus 200 meters. And how does it go underground? And then we, talk with them, and it turns out this is a thing that we need to care about. And also, other assumptions that we made, such as we just expected that the runway is flat. Like it's 3.6 kilometers in Budapest airport, which is really long. Like you don't even realize how long the runway is. And we just assumed that it was flat. Like I assumed that the entire airport was completely flattened out, but that's also not true. So the landing strips definitely have a lot of height change in them because they don't really flatten out the entire place. And also, in our visualization, we just assumed it was flat, so we just drew a flat line, and then the plane as the plane landed, even when we had the correct altitude data, it still went underground in our visualization, and we were also again looking oddly at the data, and as it turns out, yep, it's not flat. So there are a lot of things that whenever you are working on any sort of project in any sort of industry, you should ask and never sort of assume these things, because they are dangerous. Thankfully, no lives were depending on our project. But if this would be something that would have been used for real, we need to make sure that these things don't happen. So with that said, I'm going to now show you a video of the actual device in action. So on the top left, you will see the headset in the hands of our CEO, and on the display, you will see what he sees. So let's see. So you can see the airplane outside the window that he's looking at. And we also had, as you saw in the video, we had a lot of features. So besides just toggling the labels, turning them on and off, zooming in and out, we could lock the camera to an airplane. So even without you specifically having to move it, we could just track the airplane from really far away. And this was really good because the camera itself had a 30x optical zoom, and with digital zoom you could go even more. And they could see airplanes from much further away than they could have seen them with just a normal binocular, because their hands are shaking. So if you're trying to look at something that's really far away and really fast, it's really hard to track something. So that kind of solved that issue, which was nice. So this project more or less ended. We had it in the tower for like a month. and people, trialed it and everything. And then we got to the point where, okay, yeah, let's, add HoloLens. Let's see how that would work. And obviously, new device, new problems. So the HoloLens is, it's a mixed reality device. So it mixes, holograms and digital, creations with the world around you. But the device itself isn't really capable of knowing where it is in a geographical sense. Like, it's very good at understanding that where it is inside a room, and as long as you are walking around, it will know where you are. But there is no GPS in the HoloLens. There is no compass in the HoloLens. Like, there is no way for the HoloLens itself to know where you are if you are outside somewhere. So and also, not to mention, the HoloLens has no idea about tracking objects. Like, it can't see an airplane in the sky really, or it can't recognize buildings to adjust where it's looking. So we had to solve that issue, because locally in a room you could have QR codes, you could have model recognition. Like, if you have a model of the car, you could make the HoloLens recognize that it is a car and track information around it. But yeah, none of these solutions really work. So what we had to do was set a starting location in our server that, okay, every time you start with the HoloLens, this is where you're standing. And then you pick up the headstand. From that point on, you can walk around. And then we also had to calibrate where are you looking, like your orientation. So we did this by everywhere, if you were up in the airport tower, then we picked buildings. If you were in our office building was thankfully in one of the hillsides here in Budapest, so we had a really nice view of the city, and we could pick out tall buildings in the distance. So we sent these buildings out to the application as airplanes, fake airplanes, and you had to click on them. Okay, I'm looking at this, click. I'm looking at this one, click. And with that, we could calibrate where you're looking exactly. And from that point on, as you were turning around, the device would know where you're looking, and the labels and everything would be accurate. And then, just to make our lives more complicated, at the time, ASP.NET Core was sort of coming out, version 1 was released, and then they were working on version 2 already. And we knew that the framework stuff was going to stop development, so we started moving away from it. But it kind of made our lives hard, because we were using SignalR for the communication, and it wasn't released yet at the time in ASP.NET Core 2. So we sort of hosted the old SignalR from ASP.NET Framework in the new ASP.NET Core. It was sort of weird, to be honest. But just as a lesson, not necessarily jumping on the newest technology might help. Sometimes staying with something older, but it's stable, could be better. So honestly, we maybe shouldn't have jumped so soon. We could have waited a year or something. So I'm going to show you the advertisement video for the HoloLens application, and then we're going to continue from there. We called the HoloLens version of this Holo Tower. So some of the things in the video are real, even as it is an advertisement video. So for example, this part was recorded on a HoloLens, but the labels were not, because at the time when we made the video, we didn't have that working yet. Yeah, as you see, we had weather information as panels. We had the list of airplanes. We listed altitudes and speeds and everything. So, sort of got all the information that an air traffic controller would get at a at their workstation. So jumping into this, how did we evolve this camera project to the HoloLens? It's not that different from VR, because basically we had to create a model of the world, of the airport, of the nearby objects inside the game engine, and then the camera was just a fixed viewpoint. It couldn't move, but it could pan, tilt, and zoom. That's what 3 degrees of freedom means. And then the HoloLens, it's a 6 degrees of freedom device. It can move around, but it can also translate itself. It can move in X, Y, Z, go up, down, left, right. So essentially, we were doing the same thing, but we were adding 3 more degrees of freedom to the viewpoint, and we were removing the camera feed, and we were removing this black background, but everything else sort of stayed the same. We had the same labels, we had the same logic everywhere. So as we solved the problem of placing the HoloLens and figuring out where you're looking and where you are, we didn't have that much more to do. So now that we did all this, here's a video of the HoloLens application actually working and tracking airplanes. This was recorded on the terrace of the air traffic control tower. So it's like just above us where the previous video was shot. So that's like a Ryanair airplane landing right there. And then I think we will have, there you go, this one is a Wizz Air one. As you can see, the A dash, that's the altitude, that's flight level 3, so that's like 30 meters right now. And then the 128, that is their speed. I think it's like knots or miles, maybe. Really, aviation uses really weird measurements. There you go, that's another Wizz Air landing. And you can see how the label moves, but then sometimes jumps a little bit. That's when we get updates from the radar. So we were smoothing out the curve and trying to move the label as we would expect. But as we get updated information, we try to correct from the servers. So yeah, there we go. Basically, this was moving it to the HoloLens. And it was a really fun project because we also had the chance to present this in London at the Microsoft HoloLens Academy, and our company became the first HoloLens Academy partner in Central Europe when we demonstrated this. And Microsoft was really impressed because this was one of the first projects they've seen where we've connected like geographically interesting objects or far and distant objects into the HoloLens, because they were not recommending anyone to do that because there were really hard problems to solve. But I'm glad that we managed to solve all of them. So we were all managing planes at this point, and now we are going to be on a plane. And the next project that we started working on with Hunger Control was creating a heads-up display essentially for pilots on small airplanes. So if you're flying, you can fly in 2 modes. One of them is IFR, which is instrument-based, and VFR, which is visual-based. The big planes, like all the big passenger planes that you see everywhere, and cargo planes, and all of anything that's like professional stuff, that's all IFR. They have their instruments, they have to rely on them, but they are made sure that they are all very accurate and precise. And you basically fly based on those things. And then there's VFR, and this is probably the hobbyist things usually, where you can't rely on the instruments, you have to rely on your eyes. You can't blame the instruments either. And this was the target audience that we were going for, basically giving VFR pilots more information as they were flying around, like trying to give them information about tall objects, if there would be like a bridge pillar or a really tall tower, an antenna tower or something like that, giving them information about airports, giving them information about like zones in the air that you can't fly into, airspaces. Like for example, in Hungary, we have 2 airspaces that are restricted airspaces above like nuclear reactors. If you accidentally fly into those, they will actually call the jet fighters, and they will probably not ask you very often. Like they will probably ask you once to leave, and the next time they are probably going to shoot. So you have to be really careful if you are just flying around, not to accidentally fly into an airspace that's limited for you. Like you can't fly close to the big airports or anything like that. So as we did this, yet again, we encountered new and even more scarier problems. One of them was there was this magnitude jump up in the scale of the things we were doing. So before, essentially, all we were doing was, restricted to the airports, and the airport itself was like, a few kilometers, and we only cared about the things near the airport. And now we were trying to display airspaces and information that were maybe hundreds of kilometers away. And we also had to solve the problem of, everything we do so far is just trying to place a HoloLens or a device in a virtual world, figuring out where you look, and you're displaying information for you. So now you are in a moving vehicle in an airplane that can rotate itself freely, and it's also moving, but then your head inside that plane is also moving around and freely and doing whatever it does. So now we have to figure out where the airplane is in the world, and then where your head is inside the airplane, so we can accurately, display information for you. So as you can imagine, this was really not an easy task to do. So let's tackle first how we solve the scale issues. One of the big problems that we encountered was that the Earth is not a sphere. Like the Earth is Earth-shaped. They call this like a geoid. This is obvious to most people, but before working on this, I never encountered anything where where this came up before. So the issue is that the further you go with like map projections, and we get all the information with like GPS coordinates, the further you go from the 0 point, which is actually not that far from you, it's somewhere in the ocean, not that far from the coast of Nigeria actually. It gets more and more distorted as you go with like the typical map projections, like the projection you see in like Google Maps or most of the maps that you would buy, which is called WGS 84. And it's really, we got used to it, and it was really nice for navigation at the time, but it is very distorted. And I've experienced that a lot of the data we got was just simply wrong when we, tried to look accurately or display accurately where things were. Because if you just use or you just assume that the Earth is just this round globe, the things are going to be, off by even by 10 or 20 kilometers here in Hungary. So we had to make the math a lot more complicated. So this is just a small bit of the code that I adapted from, I think it was like some geography or mathematics professor who wrote this. This is the only time ever when I used actual Greek letters in code, because it looked actually simpler to see and understand. So basically, we had to write a lot of code, and we have to figure out a lot of hard questions to make sure that the positioning of everything and the data we get and all of these airspaces and everything is correctly overlaid, even if we are really far from the 0 coordinates of the Earth. And honestly, we haven't even really tackled interesting problems like what happens if you would be like at the North Pole, and what you were looking at would be a very different coordinate, but it would be still really close. Or we haven't tackled like the date line near like New Zealand, where the coordinates would suddenly switch from positive 180 to negative 180. So yeah, there were a lot of like edge cases we didn't even try to tackle, but we were really happy to get this stuff working. And then, as I mentioned, jumping up in the magnitude, this wasn't just the distances that changed, it was even the sizes. Like we have airspaces that are like literally 10 kilometers tall and sometimes 100 kilometers wide. How do you display or visualize something like that on a HoloLens that has a really small field of view? Like it's a good example we usually use that. If you haven't tried the HoloLens before, if you hold an A4 paper in your hand completely, like you leave your hand completely straight, that's like the area that you actually see. And this is a really small visibility area to try and visualize something that's so big. So the idea I came up with to solve that was, even jumping ahead, imagine if you would be in a dark cavern and you would have a flashlight. And as you shine the flashlight on the walls, you sort of get an idea of the shapes and angles of the walls. And you kind of remember that, if you do this, you swipe around and you sort of remember the shape of the thing, like roughly. And I mean, roughly is usually enough, because these are really big objects and they are not very precise. So we ended up adding this like grid effect that you see in the picture on the left side to airspaces, and then we projected this light color dot on it. So it only took up like a little part of the screen in the middle. And as you were moving your head around, you could sort of like get the shape, get the idea of these airspaces, but it wasn't something that would, completely bother you. Like in the picture, in the illustration, you can see two airspaces meeting. One of the red ones, that's one of the restricted ones where one of the nuclear reactors are actually. It even like shows, time with your current speed, it would be like 3 minutes to get there. So you should, turn around before you reach that zone. And then the third and last issue with the magnitude jump is that we were, using Unity as you would use for most HoloLens projects or most VR projects. And Unity's coordinate system, one Unity coordinate is 1 meter in the real world, in the HoloLens at least. And they use floats, like the float type for these coordinates. Now, the issue with the floats is that it is not very precise. Like if you're using small numbers and small distances, it's precise. But basically, as you can see here in the slide, that the precision is 6 to 9 digits. And that means that you can store a number precisely as long as it's like 6 or 9 digits long. So if you are trying to measure something that's 100 kilometers away, you are going to have 100,000 units because 100,000 meters, and then that was all your precision. Like anything above that, you can't really expect anything to be precise. So what happened in Unity was if you ever have two airspaces really far away from you meeting, sometimes they were like jumping ahead of each other because the game engine sort of ran out of the precision to accurately display objects that far away, especially when it was like concerning the depth, or whenever something hit the ground and we were drawing the terrain, you would see these really weird jagged edges at the bottom of the airspace where it would meet the ground. So this is not something we honestly could really do anything about, besides just like trying to like remove the world instead of moving the plane. So we sometimes tried, well, we had ideas on how we would move like the world. So we would keep the airplane itself near the coordinate 0, so we wouldn't have that many issues with objects that were far away. And as we would be flying around with an airplane and going far away from the regime, we would reach even larger coordinates and even less precision. Honestly, this was again something that we didn't end up doing, just because the tests that we were doing were good enough and local enough, and we were sort of like stopping the project at that point. But again, it's an interesting problem that you would need to tackle if you would get to that point. And then there was one problem that we actually couldn't solve, and 1 second, which was the stability of the holograms. Now, the HoloLens itself does a lot of things to make the holograms look stable for you. So as you're moving around your head, if you're just standing in the room, it automatically corrects, like little lens movements. It automatically corrects rendering. It automatically like transforms what the picture you've already rendered if you move your head too fast and your application can't keep up. So it does all this, and it's magical because the end result looks very good. But the issue with all of these solutions, or most of these solutions, is that we can't turn the stabilization features off. And the very specific one that you can't turn off is this, like the HoloLens itself renders a larger area than what you actually see. Like your application, let's say it gets rendered in this size, and what you actually see on the HoloLens is a smaller size. And they do this because as you shake your head around, they will move what visible area is, they will move this visible area to you. So you always see, something, even if your application can keep up with the rendering. But this, stability only works when you're just standing. If you're in a vehicle that's like shaking around, your eyes are not shaking around, but the device is, and the device detects this as if you would be shaking. So the end result is that the holograms and everything just, vibrates, and it's just not an enjoyable, and honestly not a usable thing. And because you can't turn this off, like this is baked into the hardware almost, we had to switch actually to a Epson, like it's like an older smart glass that didn't really do anything except just, show you whatever you put on the screen. But because it didn't have this, stability feature, which again is a really good feature if you're on the ground, we could use it for this, for this project. So now I'm going to show you a video of the project in action. It's very, very interesting. So yeah, this is shot through the lens of this thing in an actual airplane. That's a bridge on the north side of Budapest. You can see how it's like 206 meters tall, and it's illustrated by these red lines, so you don't accidentally go into it. You can see how we visualize the terrain with this grid effect. You can notice also that the update is slightly lagging. This is because the GPS data at the time, we didn't smooth it out. So these are the slow updates from the GPS, like once every second or something like that. Yeah, I think we are turning around a little bit. There we go. Yeah, this is some factory that also had like really tall chimneys. So they were also in this database. This is an airport called Tököl. That one is also an airport called Dunakeszi, and now you can see the flashlight effect I was talking about, how it roughly lets you visualize what the shape of these airspaces, and it would tell you how far you are and how much time it would take you to get there with your current speed. Yeah. It was very interesting because we were, using this device that would read the rotation and position of the airplane. It's like, imagine like a Burger King hat, just full of like AR trackers, like sort of like QR codes, and the camera looking at the person's head. And then we had a laptop hooked up to a car battery in the airplane. So it could do all the, really GPU intensive tracking. And then we fed all that into this rendering engine we built, and then that was hooked into the AR headset. And this is basically how we managed to build this. Yeah, it was a really, really fascinating problem. I think one of the coolest things I've worked on, and probably maybe one of the coolest things I'm ever going to work on. It's been really fun. There you go. You can see a really tall tower there. That's like 646 meters. It's probably like on some hill right there. Yeah. And as you can see, we also show this error, please avoid LHR 1, like please avoid the restricted airspace 1. Like we would, provide notifications and alerts to the pilots so they don't accidentally go somewhere where they shouldn't. Okay. And there we go. So as a last thought, where do we go from having all this, and just looking out into the future a little bit. So at that point, I ended up rewriting almost the entire thing in .NET Core with a new universal system to store entities. So originally when we worked on the application, we just had these airplanes flying around, and in this project you see that we had now indications for terrain, we had positions for airports, we wanted to show airspaces, we wanted to show tall objects that you don't want to fly into obstacles. So we built this generalized solution for, you can have any sort of entity, and the system will just figure out how to render it, how to store it, how to synchronize its position. We also generalized the camera systems more, the synchronization of the location, so we could have one server handling multiple clients. You could have like a PTZ camera, you could have someone flying, you could have someone with a HoloLens. They would all see the same things. But yeah, as you would imagine, there's always room for improvement. So this is just sort of just begun some of these projects as we were winding down our efforts. And then we were thinking about doing more, like looking out to the future. What else could we do? And one of the ideas that we had was generalizing this even more. Like right now, if you remember, in the HoloLens applications, we had these panels that move around, state changes. So we are thinking about synchronizing the state of the UI element, synchronizing the state of the application, maybe reintroducing, like, we've worked a lot on making sure that we know where the HoloLens is in the world, like, its GPS position and where you're looking, but we didn't really care about what the HoloLens is typically used, which is, locally in the room, where are you? And we were also thinking about reintroducing that concept. So you would have two people look at the same panels in the same room while also, looking at the real world and having that synchronized for them. So that's, interesting concepts. And then we were also thinking about open sourcing some of the work that we did, which haven't happened so far, but it might still happen in the future. If it does happen, I will definitely tweet and talk about it at that point. So I think it would be interesting to see, because some of that ideas and some of the things that we did were really cool, and it's kind of sad that all of these research projects sort of ended up as research projects and never really made it into an actual product. Yeah, so this was more or less what I wanted to talk about and what I wanted to show. So thank you everyone for your attention, and I try to leave a few minutes at the end for questions, if anyone has some.
Thank you very much, Tamás. That was amazing. I don't even know. I'm still in shock. I'm trying out everything. Was a lot of work and a lot of amazing things that you did there, which was. I don't know if there's any questions.
Yeah, I have a question.
Is there anyone with a question?
Hi, yeah. Go for it.
All right, go on.
Okay. Tamás, thank you for this interesting session. I actually learned a lot about, trying to interface the airports and GPS and the rendering and everything into the HoloLens. But you mentioned something about the initial problem you had, streaming data using Signal IR. Please, can you repeat that? Like, what was the issue you had with Signal IR initially?
Mm-hmm. So the first time we used Signal Art, we were using the ASP.NET framework, like the old, ASP.NET framework 4.7.2 or whatever it was at the time, the old Signal R. And it was working well, so we didn't actually have any issues specifically with Signal R itself. The issue was that we wanted to move to .NET Core, and when we were making the switch to .NET Core, they were just not ready with the new Signal R yet. Like, they were completely rewriting Signal R, they were changing a lot of things, and they were just like completely not ready with it. And because of that, because they being not ready, and also the HoloLens being stuck on an older Windows version that couldn't handle the new Signal R beta that they had, we had no real choice, but we had to just somehow use the old Signal R from the ASP.NET framework inside the .NET Core, which was, definitely not something that anyone would have recommended. But we sort of made it work in like an ugly, hacky way. But yeah, that was basically it. And then I think a year later or something, HoloLens finally received an operating system upgrade. And in that OS version, you could finally use the new Signal Air .NET client. So we had finally dropped the old ASP.NET Framework one and move ahead with just purely .NET Core. So that was it. There wasn't really any problem specifically with Signal R. It was more a problem that they didn't update the HoloLens operating system for like a year or something, or like 1.5 years.
Okay, then one other question I have is, was there any performance like boost or tweak in switching to the Signal IR for ASP.NET Core?
Not really, honestly. Like, it was more like we knew that Microsoft was stopping development of the old ASP.NET Framework one, and we just wanted to move ahead and not get stuck using something that wouldn't get any upgrades and updates. Because like realistically, the information we were sending is very, very little, so we didn't really have any issues doing the updates. When I did the rewrite later, like the thing I mentioned at the very end, I actually ended up rewriting the logic for any data that's like updated really quickly, such as where you're looking or airplane information, as a custom, like just a UDP message stream. So that was a completely custom thing I ended up building at the time. But we could have stayed with Signal, honestly, if we wanted to, but we were anticipating scaling out to like a lot more clients and a lot more data. So I just preemptively did that move. Yeah. I see one more question here, asking if adding a GPS sensor to the HoloLens would make your work easier. Yes, it would by a lot, but you can't. That's like the short answer. We looked into this, and the HoloLens 1 doesn't support, there's this USB OTG, which is, using an USB on like a mobile device to plug something in there. And your HoloLens doesn't support that. So you can't really connect a GPS to your HoloLens, even if you want to, unless you would, do some some Bluetooth, custom Bluetooth thing or something like that. But we couldn't really find a device like that. So we ended up just, using a PC and then streaming that information to the HoloLens. But yeah, we thought about that a lot. We really wanted to do that, but we couldn't figure out how. I think it's different with the HoloLens 2. Like, I don't think it has GPS in it, but I think the HoloLens 2 can now handle plugging things into it. I think, but I'm like not 100% sure. So that might be different there. But this was a point I raised, and I talked about to like a lot of Microsoft engineers, that we would love to have this. But honestly, they say that they don't want to add it because it uses a lot of battery, and battery life is already very critical with the HoloLens. And like, you shouldn't really, they were not intending usage of the HoloLens outside. Like the screen, it's barely visible. Like something I didn't talk about in this presentation, but we actually had to cut out these, half transparent black plastic sheets to put in front of the display when you are in the airplane, because the sun is just so bright that you can barely see anything on the HoloLens itself. So we had to like create like sort of like a sunglasses for the HoloLens, just so you can see the content on it. Yeah.
Very, very, very amazing session, and Tamás. I have one question. You mentioned the problem of the airfield not being level. Did you ever solve that, or if you did, how did you solve that?
Yeah, we actually just asked the people of the airport to provide us with an accurate plan of the airport. Like, we reached out to them, and they have like a very detailed plan of everything in the airport. Like every single little sign they have like marked it, how tall it is. So we just basically asked for the plans, and then we ended up correcting our 3D model of the airport accurately based on the terrain information they have. And we just displayed the runway correctly. Something that wasn't visible in the HoloLens video, but in the HoloLens app you could turn on a mode where if you would render the entire airport in 3D. So just imagine if you would be in the tower, and let's say you are in Dubai and there's like a sandstorm, or let's say you're here in Budapest and there's a crazy snowstorm, or there's a really thick fog and you can't see anything. You could turn on in the application to show, not just the airplanes, but show the 3D models of the airplanes, show 3D models of the buildings, the complete runways and everything. Like basically as you would be looking outside your window. So for that, we definitely had to, model everything accurately. So yeah, we just asked for the information, they gave it to us, and we modeled it.
Oh, nice.
So are there any other questions? Anybody have any other questions or anything to add?
Yeah, it looks like that was it. Yeah. Well, thanks everyone for joining and attending. I was glad I could talk little about this, because honestly, there is so much more. As you can imagine, I could talk about this for weeks. But yeah, these were really interesting and enjoyable projects. Yeah.
Thank you so much, Tamás. It was a very, very insightful session. I'm very sure you had fun working on this project. Even listening to you talk about it sounds very interesting. Thank you so much for joining us. We are so glad to have you here. I think Princess is off, probably network issues. And we are right on time. So I think we'll call it a day here. Once again, thank you very much for
Yeah, thank you
joining
for
us.
inviting me. I'm glad I could talk about this. Yeah. Thank you.
Great.
All right. Yeah. Take care, everyone. Have a nice evening, I guess. Yeah, it's sort of evening-ish now.
Yeah.
And then yeah, reach me out in the future if you have any more interesting things. I could probably talk about more things later if you need.
Of course.
Cool. Bye, everyone.
Yeah, bye. Have a nice weekend.
You too.
Israel.